Pleasure to be here. I'm going to talk about some of our work on agents, but I want to take a broader view of what's happening in AI and focus on the importance of open source. So everyone has seen some sort of figure like this, where over the last few years, the capabilities of these models have simply skyrocketed. But what's less appreciated is that the openness and access to these models has plummeted almost symmetrically. We used to have access to the full paper, weights, code, data, and now all we have is the API. It's a very good API, but it's just an API. And so the question is, why does access matter at all, right? You can do a lot of things with just the API. But I want to make a simple point here, is that access shapes research. This is something that I don't think we think about very much, because most of the time we have our heads down, we're just working on whatever problem given what we have. But if you look historically, access has really dramatically changed the type of work that has happened. So going back to the 90s, where the whole entire field of statistical NLP emerged just because we had access to internet scale data, a text and digital form. In the 2010s, there was a proliferation of these organic, large-scale annotated data sets like ImageNet and Squad, and these were available because we had crowdsourcing platforms like Amazon Mechanical Turk. And then finally, in the 2010s, of course, we wouldn't be here without GPUs. Deep learning would not have taken off. So access shapes research. So for foundation models, I'm going to talk about three types of access. The first is API access to a black box model. The second is open weight access. And the third is open source. So API access, think about it as you're a cognitive scientist. And all you can do is measure the behavior of this black box by putting in prompts and getting out responses. But you can't look inside the black box. I'm going to talk about how you can actually do a lot here. And in particular, since it's an agent class, I'm going to talk about all the interesting types of agents you can build using just black box access. Open weight access, you can think about it as you're a neuroscientist who can now poke at the internals of what's in this black box. Now, of course, real neuroscientists have it much harder than we do. But you can get a little bit more deeper access, which allows you to start to begin to understand the mechanisms behind the models and also to create novel derivatives, such as distillations and fine-tunes. But both API and open weight access, you have to remember, we're still confined to existing models, to their architectures and to their design decisions. And what we need instead is open source access. So in open source access, you think like a computer scientist who is building a system and who can control every part of it. And this gives you the opportunity to really question everything, to question the data set, to question the model architecture, to question the training procedure. You have the ability to hopefully make things better as a result. So we're going to go, in the rest of the talk, I'm going to descend this layer cake step by step. So starting with API models. So if you think about an API model, I wanted you to think about it as what I call, quote unquote, a universal function. Right? It's a function such that if you give a prompt with a natural language instruction, that function can do a lot of different things. It can summarize, it can verify things, it can generate. And that's the power of these foundation models, is that they're so general purpose. And now once you have one of these APIs, then you can start thinking about composing them into larger systems, which we can then think about as agents. And importantly, we want to think about the API as a controller of execution. So it's not the case that you have just a fixed program and then all you're doing is calling out to an API at the leaves as primitives. But in fact, the API actually controls the execution flow. It controls what the program is going to do next. So here is a basic architecture of an agent that we're going to work with through the next 10 or 20 minutes or so. And here's the way it works. So an agent takes observations from the real world, it perceives them, and adds them to a memory stream. A memory stream is going to be something that records everything that has happened so far. And because it's a digital agent, there's no reason to forget. It simply stores everything. So now there's stores too much. Now you need to retrieve the relevant memories, and that gives you a piece of context that you can use to do one of three things. You can act in the present, which means essentially tool use, grounding into the real world, taking various actions. You can look backwards, and you can reflect on your memories. This is things you can think about summarizing what you've seen so far, verifying what you've seen so far, and so on. And you can plan. You can plan for the future. And this gives agents a sense of long-term direction as opposed to just simply reacting in the moment. Okay, so with this basic agent architecture, where every one of these boxes is powered by one of these black box API, LLM APIs, we can start to build things. And I'm going to tell you two types of agents we can build. One class of agents is problem-solving agents. These are the agents that you typically think of when you think of the word agent. They solve problems. The second is going to be simulation agents, which is something that maybe not all of you have seen, but I think is really, really fascinating. So let's go through problem-solving agents. So I'm going to show you two works that we have recently on problem-solving agents. The first is ML Agent Bench. This is work with my student Chen and appeared at ICML this year. So the problem here is something that all of you are familiar with. It's you're given a machine learning problem, some data, some starter code, and an evaluator for test accuracy. And your goal is simply to build the best machine learning model you can. Okay, so what do? You write some code, you run the code, you get some log of what has happened, and then based on that, you think a little bit and revise the code, and you run the code, and so on. Okay, so this is what all of you have done. And the goal is to build an LM agent that actually does that. Okay, so this is in a slide basically what we do. So we craft this prompt. So you're a helpful research assistant. Here's the things you can do. Here's the task description. And I want the agent to reflect on the observations that it's gotten so far, make a plan of what to do next, fact check that plan, because sometimes to guard against hallucinations, think a little bit, and propose an action to take. Okay, so then that goes into the language model. The language model dutifully does the reflection, plan, fact checks, thinks, and then produces an action. And that action is something like run a script, edit a file, so on. And that produces, through interactions with the underlying environment, a observation. In this case, it's executing this train.py file and produces some log of training accuracies. And now, given that observation, it goes back into this memory stream, and where the memory stream, when we construct the prompt, we give the last three elements of the memory stream. So the memory stream has basically the full log of what has happened so far. Okay, so basically this is just, it goes in a loop. The LM calls, generates some actions, it generates some observations by executing code, and it goes back into the memory stream. So relatively, simple. We created 13 different benchmarks and evaluated a whole host of different models. And the results were mixed, I would say. The best performing model is Claude 3. And for some of the more classic Kaggle competitions, it does really well on, presumably because it probably has seen some of this in its training data. But some of the newer ones, like Baby LM, it just completely fails on. Okay, so this is a challenging, deliberately chosen to be a challenging problem. But I think it's something that I think at the cusp of what current language modeling agents can actually do. So there's actually a whole bunch of work in this area, which I think is really exciting. And the idea here is that I think of this as self-improvement. So this is not any agent benchmark. It's an agent benchmark that's aim to improve research, which means that if you solve the task, you actually get better algorithms at, you're improving the model. And once you improve the model, maybe you can solve the task better. So I think that's a kind of an interesting thing to keep in mind. So now let's talk about a second type of agent that we've been working on, one for solving cybersecurity challenges. So here is the task. So you have an agent. It's given access to a server running, let's say, at port 80. And it's also given the code that's running on the server. So it has a copy of the code locally. And furthermore, it has a bash shell, which it can do whatever it wants. Okay? And the goal of the agent is essentially to hack into the server, right? In specifically what that means is it's going to read the code, understand, and identify a potential security vulnerability, exploit that by running some sort of bash command, and then retrieving what is known as a flag, which is a secret string, to prove that it has indeed broken into the server. Okay? So the evaluation here is very, I think, clear. And these are called capture the flag competitions, which are hosted annually by cybersecurity people. And so that's a task. This is an extremely hard task. I don't think I could do this very well. And to make it a little bit easier, we have the option of giving the agent a set of sub-questions which attempt to break down the ultimate task into a bunch of different sub-steps where we can measure, hopefully, some partial progress. Okay, so the way we build an agent to solve this these cybersecurity tasks is essentially the same recipe as we use for the ML agent bench. So you ask the agent to reflect, make a plan, think, and execute a command. Now that command returns some, after the execution, some observations are returned, and that's used to update the memory stream. Okay, so it's a very general recipe that you can see applies to a bunch of different, quite radically different agent problems. So how do the results look? So we benchmarked a bunch of different models, and the best performing model is, again, Claude 3.5. It solves 17.5% of the benchmarks. And the interesting thing is not all the benchmarks are the same. The hardest benchmark in our task in our SciBench took a team of humans 24 hours to solve. And these are people with cybersecurity experience. They're not just random people. They're competitors. And the hardest task that the best model was able to solve to date took humans 11 minutes. So quite a bit of gap between what humans can do and what the best models can do. But again, this gap is shrinking over time. Okay, so again, this cybersecurity benchmark is interesting, not just because it's a difficult and interesting agent benchmark, but also because of two reasons. One is that there is a tremendous amount of wonder and interest in understanding the risks of AI, in particular with relation to cybersecurity. So is it the case that once you develop frontier models, now we have these enormously powerful agents that can basically break the internet? And so from that perspective, AI policymakers are really interested in the question of risk assessment. And this benchmark provides a quantified way of thinking about risk. On the other hand, there are cybersecurity people who routinely build penetration testing tools. So these are tools which try to identify and break code before deployment so that you can fix the problems before you put the server up. And so these folks are really excited about this work because now we suddenly have much more effective penetration testing tools. So far, I've shown you with a fairly simple prompting strategy, you can build problem-solving agents in both ML engineering and cybersecurity. Now let's turn to building simulation agents. So this is based on a paper by June from last year. And the goal is, can we simulate people or human behavior? So in order to do that, we built a virtual world which we called Smallville, and there are 25 agents. Each agent is powered by LLM architecture, which models this architecture. In fact, this figure comes from that original paper, which we've sort of repurposed over and over again for all our agent projects. I'm going to focus on two pieces of this. So retrieve and reflect. So remember, the memory stream remembers everything that happens. And if you think about a human, you're like yourself, you're wandering around, most things that you experience are fairly mundane, but nonetheless, they all go into the memory stream. So the memory stream has something like refrigerator is idle, or desk is neat and organized. So hardly remarkable things to write home about, but you never know what you're going to need. And that's why we store everything. Now the problem gets kicked to at sort of inference time, where you need to make use of this memory. You can't put everything in the memory stream in your prompt, so you need to retrieve. So we retrieve based on 3 criteria. One is recency. So things that happen in recent memory are presumably things that you should pay attention to more. Importance, which is events are generally marked with some sort of intrinsic importance. Like desk is idle is not very important, whereas if you got married, that's probably pretty important, I would hope. And the third thing is relevant. So based on the current context, which things are relevant? So for example, if you are looking for your water bottle, then maybe the memories of where the water bottle has been is now suddenly much more relevant than it would otherwise be. Okay, so with these 3 factors, we do retrieval to slim down the memory stream dynamically to a much smaller set. The second thing I want to mention is reflection. So remember, the memory stream is very, very low level. And if you have an agent that just reacts to individual memories, that's going to be an agent that is going to be fairly sort of in the weeds. So reflection takes groups of memories and abstracts them. So for example, we have this guy in the Smallville whose name is Klaus Müller. He's reading about urban design. So that's a concrete observation. But then it gets abstracted again and again into something high level, like Klaus Müller's highly dedicated research. So this is what gives the agents a more global sense of purpose rather than reacting to low-level details. Another thing I think is really important about modeling humans is that humans are social animals, and they talk to each other. And so our agents also talk to each other. So in one instance, Isabella is planning a Valentine's Day party. She tells all her friends about it. And then those friends continue to spread the news to other people. And sometimes the news comes back to Isabella. And so one thing that's really interesting about the simulation that we observed is how information diffusion is modeled through the multi-agent simulation. Okay, so one problem with this generative agents is that it's all made up, right? These are not real people. These are just little, avatars running around in this virtual environment. So, but the true promise, I think, of this technology is, can we simulate actual real people? So what does that even mean? So this is a paper that we just put out on arXiv, so as of like today or yesterday. And this is our attempt to make it more real. So again, led by my student June. And the key insight here is interviews. Because remember, people are very rich, and how do you pack an individual into an LLM agent? So interviews have been used as a tool in the social sciences and for quite some time to capture a lot of rich information about people. And so when we're doing these pilot studies, an interviewer was asking June, to start, tell me the story of your life, starting from the beginning. And June talks, well, I was born in Korea, I moved to Boston, and then then the reviewer follows up dynamically and asks, like, oh, tell me about what it was like transitioning to Boston from Korea. Well, moving into a different country is really a heavy lift and so on. So you could see that the interview content actually captures enormous amount of information. It captures not only the factual content of what actually happened, but also the perspectives and the personalities of the interviewee. And so what we did here was to try to scale this up. So we sampled 1,000 people, demographically diverse from the US. We had each of them go through a 2-hour audio interview with an LLM agent, of course. And this produced an interview transcript. That interview transcript now becomes the seed of the agent memory. Okay, so now we have for each human over here, a corresponding agent over here. So we have 1,000 humans, 1,000 agents. And the question is, how close are the agents to the actual corresponding humans at the individual level? To assess this, we ran a battery of surveys, games, and experiments, which are taken from the social sciences, economics, psychology, and we ran the same exact experiments on the humans as on the agents, and then we're just comparing, do they match or not? Okay, so this is a very nice quantitative way to answer the question, are these simulated agents actually behaving like people? And a very quick snapshot of the result is that, yes, by and large, the agents are able to capture humans. Of course not, completely. One, I think, confounding factor is that humans are themselves not consistent. So if you asked humans to do these surveys, and then you ask them 2 weeks later, they're only 81% of the time matching themselves. So that's just sort of a skyline of how far you can get. And now you have these agents based on GPT-4o trying to answer the same questions, they get around 69%. So you can think about this as you're capturing 85% of the total accuracy, where baseline is something like in the 20s. So this is not bad. And we see that if you don't use the interviews, it's worse. So the interviews do actually capture a tremendous amount of richness. Okay, so let me reflect a bit on black box API access. So we can do a ton with just black box APIs. You can create all of these agents to solve complex problems in ML engineering and cybersecurity, and also to actually create simulation agents. And you can think about this as really building an approximate digital twin of society. So social scientists are actually really excited about this tool because it basically provides an in vitro laboratory for them to run experiments. And you can go to do cool things like give the same agent the control and a treatment, and then measure the difference. So, and you can, we have 1,000, demographically diverse, so you get sort of breadth. Now, of course, it's important to remember that these are not real humans, and your mileage might vary depending on what your questions are asked. But this technology, again, is getting only better. And as long as we're being grounded and realistic in our expectations, I think this is going to be a very powerful tool. So one thing that I think is lacking so far is that so far these agents have been static. We've taken off-the-shelf language models, such as GPT-3, 4o, or Claude, and we simply prompted them. And what we really like these agents to be able to do is learn from experience. This is what humans do. We're not static. So you can think about this analogy of where we are with AlphaGo. So remember, AlphaGo had 2 phases. One is supervised learning on top of human games, and then followed by reinforcement learning where or sort of self-improved. And I think we're, for LM agents or language models, we're sort of here right now, where we've invested over the last 4 years quite a bit of energy in terms of pre-training these very, very powerful models. And now we're beginning to build agents. And one opportunity I see with agents is not that only that they can do interesting tasks, but they also present new opportunities for improvement. Because once you have an agent that's operating somewhere in an environment, it can presumably get some sort of reward signal. And with that reward signal is now you're off to the races in terms of improving the agent. So I think it's a lot of exciting stuff to come. But in order to do all that, you need deeper access to models. You can't just have the black box API anymore. So let's now descend the layer cake into open weight models. So what is an open weight model? So technically, these are more accurately, they're called dual use foundation models with widely available weights. This terminology comes from the executive order from last year. It's a bit of a mouthful, so I'm going to use the term open weights. And just as a kind of a technicality, but an important one, the reason that they're widely available as opposed to just available is that the licenses of these models, including Llama, have restrictions. For example, if you have 700 million monthly active users, then it's not open to you. You have to get a special license from Meta. Okay, so one immediate off the bat advantage of open weight models is reproducibility. So how many of you have run experiments on TextDaVinci 003 or 002? Okay, so some of you, and well, too bad because it's no longer available. So one problem with these API models is that you don't control them, and once in a while they just disappear, which is really bad from reproducibility because now you can't reproduce any of those experiments that you had done before. Whereas if you had the weights, you can just store them on your laptop, under your mattress, wherever, and where they'll be safe and they're forever. Okay, so what can you do from a research perspective with open weight models? I'm going to give you a few examples of some of the types of research you can do. So this is, much of this is not my work. So this is work by folks from Transluce. Apparently, if you ask Llama 3.1 AP instruct this question, which is bigger, 9.8 or 9.11? It will reply 9.11 is bigger than 9.8. So if you're paying attention, this is actually incorrect, I think, right? Right, everyone? Okay, good. So if you just had an API model, you'd be scratching your head, like, why is this language model being so ridiculous? But if you have open weight, you can open up the hood, and then you can try to figure out what's going on. So this is what the Transluce folks did, which I think is really cool, is that for every single neuron, they looked at the examples that trigger that neuron and use that to create a summary of that neuron. So now, if you can, there's a cool interface you can go play with online, where you mouse over 11, it shows you that 11 is triggering this neuron that fires in references to September 11th. So now you think, oh, okay, I think I know what's going on, is that this is getting interpreted as a date or somewhat as a date. And if they're dates, then 9/11 is after 9/8. Okay, so by looking inside, you can actually get a much deeper insight into the inner workings of these models and debug some of these mysteries. They also have some examples you can see online where you have a model that refuses to answer a question, but then if you look inside, it clearly knows the answer and is not just refusing to tell you. Okay, so here's another fun paper from NVIDIA where they took a 15 billion parameter model, pruned away some of the layers, and resulted in an 8B and a 4B model with minimal drop in performance. So I think that this is one instance, I think, of a larger trend that I think is really interesting, where you have big models that we have trained, but in order to use them, you need to make them smaller. And so the question is, how do you take the power and modeling capability of a larger model and sort of push it into a smaller model? And I think it's relevant for agents because agents, remember, you need an API in the inner loop of perhaps doing some more complicated task. And you want potentially your APIs to be much faster than just doing a one-shot query of an API. Here's another project that I think was really impactful, which is adversarial attacks. So these authors took Llama and optimized for a prompt that essentially tries to jailbreak it to get the model to do malicious things. And for this, you need open-way access because you need to look at the gradients through the model, which is something you can't do with like GPT-4o. And you optimize over these the prompt, so that's fine. But the really mind-blowing thing is that you take this prompt that is optimized for Llama 3, and then you just take it and put it into the prompt for an OpenAI model. I think this is GPT-4. And it actually jailbreaks GPT-4. So this is really fascinating because there's something sort of really deep and mysterious about the transferability of these attacks. And also it goes to show that open-way models, access to open-way models actually have implications on closed models because it tells us something about closed models because of transferability. Okay, so next I'm going to tell you a little bit more about one particular project that we've been doing with my students Sally, Ahmed, and Rohit. And this is a project that is definitely uses open-way models, but not only that, it exists because of open-way models. And I'll explain what that means. So if you go to Hugging Face, you'll see that there are a ton of models out there. And some of these models are fine-tuned on the same foundation model, and some of them are not, or at least it's claimed that they're not. And so in general, you have these sort of a zoo of models, and you want to understand what is going on. What's the relationship between the models? Because often documentation is poor, and people might be trying to mislead other people and so on. Okay, so concretely what this boils down to is a model independence testing problem. You're given two weights, sets of weights, and you're asked, were these independently trained or not? Full stop. And in particular, if they're not, it could be that one was fine-tuned from another, the theta 2 was fine-tuned from theta 1, or they're both fine-tuned from a common model. We don't distinguish those cases, but what we're distinguishing is between just full independence and not independent. Okay, so I think this is very clean. So how do you solve this problem? Well, and a first idea is that you might just take the weights and just compare them. Compare some cosine similarity or some sort of similarity metric. And for NLP weights, this means just taking the rows and computing cosine similarity and averaging. So this, gives you a number. But the problem with this is that, well, if you get 0.1, does that mean they're independent or not? I don't know. Are there any, guarantees? It's not clear where you set the threshold, and does the threshold depend on the model architecture? It's not very rigorous. But this is the sort of the kernel of something we're going to turn into actual rigorous test. In order to do that, I'm going to introduce a thought experiment. Suppose you knew how theta 1 was created. It was created through this train function given some random initialization of the parameters. Okay, so what I'm going to do now is I'm going to just retrain a bunch of copies of theta 1. Okay, in practice, we're not going to do this, but thought experiment. And the idea is that if theta 1 and theta 2 were truly independent, then this similarity metric should look basically like the similarity metric of another random copy. Okay? But if these were somehow very correlated, then this would look very different. So based on this insight, you can construct an actual p-value for the hypothesis test of whether theta 2 and theta 1 are independent by simply looking at the fraction of times that this independent statistic is actually more extreme than the statistic that you actually observe with theta 1 and theta 2. So this, in its essence, turns a statistic into a threshold that gives you a formal guarantee. Okay, so now the problem is that, well, you don't know how theta 1 came about because you were only given the weights. You can't actually execute this. And furthermore, even if you knew, you probably wouldn't want to train, spend millions of dollars training this model over and again just to do this test. But we can do something here. And the goal is to fake it. So we're not actually going to train the model, but we're going to sort of pretend we did. And the idea is leveraging the sort of natural symmetries of the model. And so we're going to define perm of theta as you're going to permute the hidden units defined by theta. So like this. So take a matrix and permute the rows. And the idea is that when you permute, that's kind of like a counterfactual. That's a model that could have arisen. Now, I didn't actually train from scratch to get it, but because of symmetries, I could have started with a different initialization and also gotten to that model. So it turns out you can actually compute a p-value using this statistic as well, and this is actually a working, very efficient, algorithm. Okay, so in order to validate this approach, we looked at the subset of Hugging Face models where we sort of understood what ground truth was. So in particular, models around Llama 2 and their sort of replications. And we looked at running this test on models that were truly independent, and we see that the p-values are all over the place, which is what you want. P-values are supposed to be uniformly distributed if under the null. And if they're not independent, then the p-values are actually minuscule. So you ask about statistical significance. Well, this is like kind of blowing out of the water. This is like actually underflowing to the significant to the point where it's underflowing. So this is a very strong test. And it's sort of kind of a smoking gun that these were actually not independent, which is true because we know that these models are fine-tunes of Llama 2. Okay. So more fun things we can do. So earlier this year, there was a controversy around this mysterious model, MIQ, that appeared on the internet, and people suspected it was a leak that was Mistral fine-tuning Llama 2, and eventually the Mistral CEO said yes, it was a leak model, and indeed we were able to verify with our tests that indeed these two models are not independent of each other. We also were able to show that striped hyena, which is a model, was derived from Mistral. And then finally, Llama 3.2, their 3B model, in their blog post, they say that this is derived from Llama 3.1 8B. And we also verify that indeed these are not independent. But moreover, what's I think really interesting is that our test not only gives you the single bit of information whether two models are independent or not, but actually tells you which layers were derived from which layers. So we were able to show that certain layers of Llama 3 8B were used to create the 3B model. So this is information that actually wasn't included in the actual blog post, which is kind of a cool bit of reverse engineering there. Okay, so some reflections on open weight models. So it's very clear that open weight models such as Llama 3 have been immensely valuable for research. I only showed you a small fraction of all the papers that have been using Llama 3, and I'm sure some of you are using it in your own research as well. So it enables research on interpretability, different fine-tuning techniques, distillation, model merging, and furthermore, you get all these nice reproducible guarantees and not having to worry about model deprecation. One, I think, interesting thing about open weight models is that you're making these very sort of arbitrary changes to the weights by averaging them, by taking out layers, and they're sort of kind of crude in a way. And the question is, how do these on Earth yield any sort of functional changes that are coherent? And the answer is that there's no guarantee of this. And in general, you actually have to go back and fine-tune your model and sort of heal it after you sort of rip out like half of its layers. Open weight models also teaches us about API models, and it also opens up new types of problems. For example, this model independence testing problem, we wouldn't have worked on this problem if it weren't for open weight models at all. So, but at the end of the day, we're still confined by the blueprint of existing models. So all these models are still transformer architectures. They're still the particular set of weights that Meta has, given us. And so in order to go deeper to open source, we need to, open up the hood more. So fortunately, there's a lot of open source language model efforts from Luther to AI2 to Hugging Face and so on. And each of these is trying to create open source models. The downside is at this present moment, the open source models are far weaker than the strongest open weight or API models. But what exactly is open source? So a little bit of kind of historical context. Open source clearly comes from the term open source software, and open source software and free software have had a long history in computer science, stemming from the roots in MIT in the 50s, the hacker culture, and its idea in academia where you do open science. These are sort of the roots that inspire open source, and it has coalesced into these values of creativity, exploration, transparency, collaboration, resistance against authority. So this sort of defines what open source sort of stands for. And of course, there's famous figures like Richard Stallman and Linus Torvalds that created this whole ecosystem around GNU Linux, and that led to the open source initiative founding in '98, which finally defined the term open source. And so open source was practiced long before the term open source software even was defined. And now OSI is now trying to define what open source means for AI. And it can be summarized in terms of 4 freedoms: the ability to use a system without asking for permission, the ability to study, the ability to modify, and the ability to share. Okay, and in more detail, open source definition requires that the model parameters be available. So this is open weights, but without restrictions. That the code be available. And here the code importantly means not just the inference code, but the training code and also the data processing and filtering code. Because the data is actually a vital ingredient in determining the behavior of these models. And without the knowledge of how the data was constructed, you can't really be truly open source. And finally, there's data information. And so you might ask the question, why data information and not data? And the answer is that you don't want to get sued. And basically, the longer version is that most foundation models are trained on web data. And web data is, sort of anything goes. Most of it's copyrighted, or at least it's not clear that it's not copyrighted. And so model developers don't actually own the license to redistribute the data. So there are some ongoing lawsuits that are going to settle, hopefully, next year or something, that are going to rule on whether training on this data is fair use. But even if training is fair use, you still can't redistribute the copies of someone else's book kind of verbatim. Okay, so another piece that I think is critical is the ability to modify. And I would say that compute is an important ingredient here. So this is not technically part of the open source definition. Nowhere does it say you need to compute. But in order to achieve the spirit of being able to modify a system, it's clear that you need compute. Otherwise, you have this thing and you can't actually, if you want to change the data, well, you need to kind of retrain at least, or at least do continued pre-training or something. So I'm going to talk about 3 projects that we've done that really require deep access to the kind of full training process and the weights and the data and so on. So the first paper, I'm just going to go these very briefly, so there's not going to be too much detail here, is the question is, what mixture over data sources do you use? So language models are typically trained over some combination of Wikipedia, books, web, code, and so on. And usually people just set the weights sort of, magically, 0.2 books, 0.4 code, looks good to me based on vibes. But we created a procedure based on distribution and robust optimization, which automatically tunes these mixtures, and we show that this performs 2.6 times faster, or trains a model 2.6 times faster than manually specified weights. So in order to do this research, you clearly need to be able to train models from scratch. A second project we did was on developing a new optimizer based on second order information, and particularly to look at the diagonal Hessian with some clipping. And this provides a 2x speed up over Atom. And again, of course, in order to do this research, you need to be able to train from scratch to show that you get improvements over some Atom. And the final project we did was on producing another architecture, an alternative to a transformer that is not as monolithic and is more interpretable. So it's called the Backpack Language Model. And without going into any detail, this model architecture allows for precise model editing. So you can take a language model and you can sort of, with a test time intervention of some hidden units, get the model to edit it into a world where it believes that the MacBook was created by HP rather than Apple. Okay, so all this is nice and well. So we touched the learning algorithm, the architecture, and the data, recipe. Now, I often get this question: would these results hold if we scaled up? And really, what this question is asking is, how do you get the compute to even answer that question? And so for this, I think this is where open source, I think, is really at is really kind of bottlenecked. And so I'll give you 3 sort of suggestions on how we might deal with the compute problem. The first is that use scaling laws. Okay, so typically you think about scaling laws as telling you about bigger and bigger models, right? But one thing that I think scaling laws could be made to do, but certainly I don't think they do this very well, is sort of extend in the opposite direction into a smaller regime where you can operate in a smaller scale model with a belief or the hope that whatever you do down here, different data, different architecture, is actually going to scale up to larger scales. And this is a way that I think you can work at small scale, but with a mindset of scaling up. Okay. Second is there are actually a lot of idle GPUs, everywhere. So most of the time, people always complain, not enough compute, not enough compute. But there are pockets of times where there is idle compute. And so if we were only able to harness all of this globally, we could actually, there's probably quite a lot of compute available to do certain things. And one technical hurdle to this is that the interconnect speed, when you're looking at decentralized compute, is just horrible. It's at least 2 orders of magnitude worse than it is in a data center. And training large foundation models requires fast interconnects. 2 years ago, we had this paper which showed that with some amount of clever scheduling and some sort of low-level systems work, you can actually train 1 billion parameter models at the time in a way that's only 2 times slower than if you were doing it in a data center, even though the interconnects were 100 times slower. Okay. So this is promising, and since then there's been a lot of work, including Diloco from DeepMind, showing a better, an algorithm to do this. And there's been even this effort from Prime Intellect where there is a decentralized training effort happening of a 10 billion parameter model where anyone can just pool compute into this massive pool. So I think this is really exciting to see how far you can get with decentralized compute. Okay, so track number 3 is basically ask for more money. And so there's the NARE, the National AI Research Resource, which has a pilot that is trying to get more compute to fund a public academic AI research. And hopefully, well, the pilot I think is ending, but hopefully this will be renewed, and hopefully we'll be able to see more of this. It is worth noting that other fields kind of have figured this out, right? And by it, I mean being able to harness, advocate for the funding of massive infrastructure projects. For example, the Human Genome Project, in James Webb Telescope, the LHC. These are multi-billion-dollar projects that are in service of open academic research, right? Not just for commercial gain, but for open academic research. And the idea is that the types of problems that you would solve if you were structured in sort of this public domain is different than what the OpenAIs and the Anthropics would do. Okay, so just to conclude, we've talked about the 3 different levels of access. I think underlying theme here that I want to stress is that access shapes the research, right? So if you have API access, there are a lot of interesting things you do. And we've been doing a lot of these things, building all sorts of different agents. With open weight models, you can do a lot more. You can fine tune, you can do distillation, and you can do a lot of interesting things with open weight models as well. But I think it's important to recognize that our research lives more and more today are living within the confines of the APIs and fixed weights. And in order to make, I think, fundamental progress, we need to question more things. We need to be able to question the data, the model architecture, the training algorithm, in order to make more progress and not be stuck in this local optimum. And the eventual goal is to really understand the mapping between data and model architecture to model behavior. And this is hard, even if you have full access, right? In the 2010s, we were complaining about how hard deep learning was to understand. And now things are a lot worse when you only have API access. There's no hope. So at least if we can get open source access, we have some hope of answering these sort of deep fundamental questions about AI. And of course, compute is a big challenge here. I think there's still a lot of things you can do at small scales. I think you can do things at small scale, but with a mindset of scale. And also, I think it's really interesting to think about how we can do decentralized pooling of compute so we can do more together than we can do individually. Okay, with that, I'll conclude and take any questions. Thanks.